Welcome to another Earth Science podcast. I'm your host, Mr. Buss, and this podcast will discuss more data that supports plate tectonic theory. So the first thing we'll look at are earthquakes. Earthquake data is a major supporter of plate tectonic theory. The image below is the aftermath of the 1906 San Francisco earthquake. It is still, as of today, the most costly natural disaster in California history. 3,000 people died in this earthquake and 28,000 buildings were lost, mostly due to the fire that resulted after the earthquake. Earthquakes themselves aren't usually the killer. It is the fire that results after earthquakes that are the most deadly. San Francisco lies along the San Andreas Fault, and the fault zone alone produces about 10,000 earthquakes a year for California. Had this major earthquake in San Francisco not existed or not occurred, then likely what you would find today in California is that San Francisco would have become the major metropolitan area instead of Los Angeles. But after this earthquake, a lot of companies, a lot of businesses did not want to rebuild in San Francisco, knowing or thinking that this type of thing might be occurring in the future as well. All right, so then what is an earthquake? So what is an earthquake? An earthquake occurs when the land shifts. The seafloor spreading that occurs in the oceans causes land to undergo tremendous stress, and as the stress builds up, the pressure becomes greater and greater until the land buckles and finally gives, and that's a fault, and that is when an earthquake occurs. And there's various types of ways the land can shift. It can shift up or down. It can shift side to side. And the picture on the right, I love this picture, so cool. It shows this where the fence used to align, and then they just kind of put some lines in between there. So that is what an earthquake is. And again, the term would be fault. Fault is where the land actually rips apart. It's important to understand that the Earth is actually rather elastic. As seafloor spreading occurs and the Earth shifts around, the ground, the rock actually can stretch a little bit. And so you'll get, for example, if this were a road here, you get the road to have a little bend in it, and then boom, at the point of an earthquake, that is when the rock actually rips apart and the stress is relieved, and you will see the fault line. So the longer the Earth goes without breaking or ripping or causing a fault, the bigger the actual earthquake and the fault will be. So perhaps it's better to have many small earthquakes than it is to have one earthquake that is massive, shifting tons of earth at a time. So we've discussed what is an earthquake. We talked about the fault lines that occur at an earthquake and how the Earth is elastic and elastic rebound theory. All right, so where on the planet do we see earthquakes, and how does it correlate to plate tectonic theory? Well, we see a lot of earthquakes along the Ring of Fire. The Ring of Fire is a ring of volcanoes along the Pacific Ocean. Why do we see a lot of volcanoes and earthquakes in this area? Well, probably because we have a lot of plate boundaries occurring in this region, where plates crash into other plates, you're going to have earthquakes. So when land crunches into land, when you have two plates converging on each other, one of them will lose the battle. In this case, it will subduct and go under. When that happens, there's going to be an earthquake, and as the land subducts over and over and over again, you get melting and you get volcanoes, hence the Ring of Fire. A lot of volcanoes, because in this region, in the Pacific, you have a lot of plate activity where one plate is subducting or going under another plate, and that's where you're going to get volcanoes and earthquakes. And the San Andreas Fault actually runs along this Ring of Fire, and the San Andreas Fault happens to be a transform fault, which we'll talk about later. It's where the land slides across the land instead of land going under and getting volcanoes. So where do we see earthquakes? We see earthquakes along plate boundaries. If you take a look at the plate boundaries and superimpose them over our earthquake data, you can see how plate boundaries and earthquake data correlate to one another. Oops, I kind of superimposed that incorrectly. This is kind of a better image here. So again, you can kind of see this pretty well, how the earthquake data correlate pretty well to the plate data. So we see earthquakes along the Ring of Fire. We see earthquakes at the mid-ocean ridges. And earthquakes help us determine plate boundaries as well. And so here are the tectonic plates of the world. You'll need to memorize these for our next test. Just kidding. I think this is just super cool that we can actually use satellite GPS data now to accurately monitor and measure the millimeters and centimeter movements of plates as they are gliding across the surface of the Earth. And every year, as we get more and more data, it just becomes more and more accurate, and we have a really, really good understanding for which direction and at what speed plates are moving. I just can't believe how cool that is. Kind of a neat phenomenon is, as plates move, sometimes they move over what we refer to as a fixed hot spot. And the Hawaii Island chain is actually a result of plate movement, the Pacific plate moving in a direction over a stationary hotspot. So the hotspot is basically providing magma and creating a volcano over the plate at that spot. And you find the next oldest volcano would be there, and then the next oldest, and the next oldest. And so what you end up with is a chain of islands that show the plate movement over a fixed hotspot. And so what this really does is this gives us an indication as to the direction the plate moved over time. It's a recording locked in time of plate movement. And it's worth briefly mentioning Yellowstone is another hotspot. Yellowstone actually sits above a hotspot that has erupted catastrophically, major supervolcano 3 times, 2.1 million years ago, 1.3 million years ago, and 640,000 years ago. You might notice that is actually a pattern, and Yellowstone may never erupt again, but it also is set to erupt potentially in the not-too-distant future. Remember, that's geological terms. That's probably not going to be in our lifetime. So you can track Yellowstone just like you track the Hawaii Island chain. Here's where Yellowstone is today. Here's where it was 6.5 million years ago, 10 to 7 million years ago, and so on. So the North American plate has been moving in this direction. And that concludes this podcast on earthquakes, volcanoes, and more data that supports plate tectonic theory.